And now in this lecture we'll answer on two questions. In the first question we'll find out the area of this green shape that is inside square ABCD. And in the second question we'll find out the area of this green shape that is inside quarter circle AOB. So we start with the first question. In the drawing we have square ABCD. You know that this is angle PQC, that is a right angle. This is line segment PQ, that is equal to 2 units in its length. This is line segment QC, that is equal to 3 units. Again, our mission is to find out the area of this green shape. So first of all, we know that all those 4 angles inside square ABCD are right angles. So write it down. This is a right angle. This is a right angle. This is also a right angle. Finally, this is also a right angle. In addition, we know that all the sides of square ABCD are equal to each other, so we define one side as A, so all the other 3 sides must be also equal to A. So here, side AD of this square ABCD equals to A units in its length according to our definition. Therefore side AB also equal to A units in its length. Side BC equals to A unit and side BC equals to A unit in its length. We define this line segment QB as X. So what is the missing line segment AQ? From the drawing it is very easy to see that AQ equals to AB minus QB. So write it down. AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X units in its length. This is line segment AQ is equal to A minus X units. In the next step, we'll define this angle BCQ as alpha, and we focus on this right triangle QBC. In the right triangle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. AB is one side of square ABCD, and therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to the rule that states that the sum of the angles on one side, according to rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle is equals to 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q, exactly according to rule 3. In the next step we focus on this right small triangle APQ, the small right triangle APQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the same rule, that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy this right angle APQ and this right angle QBC in the new page, and we prove that those two right angles are similar to each other according to angle similarity rule. So actually those are the two right angles that are going to the original domain. So those two right angles are similar to each other. First of all, this right angle QBC, this angle equals to 90 degrees minus alpha, this angle equals to alpha. So why those two right angles similar to each other? First of all, those two angles they are both equal to alpha, therefore they are equal to each other. So actually this is angle AQP. In the right angle APQ, and it is equal to this angle, this is actually angle QCB. In the right angle CBQ. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle QAP. In the right angle APQ, and it is equal to this angle, this is actually angle QBC. In the right angle QBC. So they are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle APQ. In the right angle APQ, and it is equal to this angle, this is actually angle BQC. In the right angle QBC. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I can prove that all the three angles in this right angle APQ are correspondingly equal to all the three angles in this right angle QBC, and therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. The right angle APQ is similar, this is the sign of similar, to the right angle triangle QBC according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP in the right triangle APQ over side QB in the right triangle QBC is equal to side AQ in the right triangle APQ over side BC in the right triangle QBC, and it is also equal to side PQ in the right triangle APQ over side QC in the right triangle QBC. And again, we will derive that AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we limit the CTs. Over QB is X, and it is also equal to AQ is A minus X, over BC is A, and it is equal to PQ, that is 2, over QC, that is 3. So in total, according to equation 1, we actually found out that AP over X equals to A minus X over A, and it is also equal to 2/3. Those two expressions are equal to each other. Therefore, we create equation 1, the first equation from those two expressions that are equal to each other. That is to say, according to equation 1, we get that AP over X equals to 2/3. According to equation 1, AP over X equals to 2/3. Here we multiply this equation 1 by X, and finally we get that according to this equation 1, AP equals to 2/3 X. But again, according to equation 1, we found out that AP equals to 2/3 X. We continue to focus on this long equation. Those two expressions are also equal to each other, so we create equation 2 from those two expressions that are equal to each other. So according to the second equation, we get that A minus X over A equals to 2/3. So I write it down. According to equation 2, according to equation 2, A minus X over A equals to 2/3. Here we cross multiply this equation 2, and when you get it, according to this equation 2, 3 times A minus X equals to 2A. We'll open the brackets on this side of this equation 2, and get that 3A minus 3X equals to 2A. We subtract 2A from this equation 2, and when we get it, according to this equation 2, 3A minus 2A is A, so A minus 3X equals to 0. Here we add 3X to this equation 2, and when we get it, according to equation 2, A equals to 3X. Repeat again, according to equation 2, we found out that A equals to 3X. In the next step, I'll copy the right triangle QBC in the new page and we'll implement the Pythagoras theorem on this right triangle, triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. Actually, this is the right triangle QBC that I got from the original drawing. Here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. QC, the hypotenuse QC is 3, therefore QC squared is 3 squared, that is 9. And it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total we found out that according to equation 3, 9 equals to x squared plus x, 9 equals to x squared plus a squared. This is according to equation 3, but according to equation 2, we already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. So I write it down. So we substitute a squared in this equation in equation 3 by 3x squared for this equation in equation 2. We do it now and we get that according to equation 3, equals to x squared plus a squared, and a squared according to equation 2 is 3x squared. So in total we found out that according to equation 3, 9 equals to x squared plus 3x squared. So 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So in total we found out that according to equation 3, 9 equals to x squared plus 9x squared is 10x squared. So according to equation 3, I found out that 9 equals to 10x squared. Here we divide this equation 3 by 10. And finally we get that according to this equation 3, x squared equals to 9 tenths. So here we take all of this equation 3, and we find out that x equals to the square root of 9 is 3 over the square root of 10. So in total we found out that according to equation 3, x equals to 3 over the square root of 10 units in its length. According to equation 2, a equals to 3x, so a equals to 3 and x is 3 on square root of 10. So in total a equals to 3 times 3 is 9 over square root of 10. The total we found out that A equals to 9 over square root of 10 units in its length. So return to equation 1. According to equation 1, AP equals to 2 curved x. So actually AP equals to 2 thirds x, and x is square root of 3 over 10. X is 3 over square root of 10. Again, AP equals to 2 thirds x, so AP equals to 2 thirds x, and x is 3 over square root of 10. So here we have 3 in the numerator and 3 in the denominator, so 3 get cancelled. Finally, you get that AP equals to 2 over square root of 10 units in its length. AP equals to 2 over square root of 10 units in its length. According to equation 2, A equals to 3x. So according to equation 2, actually found out that A equals to 3x and x is 3 over square root of 10, so we already found out that A equals to 9 over square root of 10 units in its length. So this is the side DC is equals to A according to our definition. Just like now found out that A equals to 9 over square root of 10 units in its length. And we already found out that AP equals to 2 over square root of 10 units in its length. So what is the length of PD? From the drawing, it is very easy to see that PD in total equals to AD minus AP. So PD equals to AD minus AP. And again, from the drawing, it is very easy to see that PD equals to AD minus AP. So PD equals to AD, that is A, and A is 9 over square root of 10, minus AP. AP is 2 over square root of 10. So in total, PD equals to 9 over square root of 10 minus 2 over square root of 10, that is actually 7 over square root of 10. So in total, we found out that PD equals to 7 over square root of 10 units in its length. So I write it down in the original drawing. This is 970 PD. It is equal to 7 over square root of 10 units in its length. Our mission is to find out the area of this green shape. So in order to find out the area of this green shape, we join points P and C together by a straight line. By joining points P and C, we can add here 2 right angles. The right angle PDC, this right angle PQC. So actually, the green shape consists of those two components, the right angle PDC and the right angle PQC. And therefore, the area of this green shape must be equal to the sum of the areas of those two right angles, because it consists of those two right angles. Write it down. We should find out that the area of the green shape is equal to the area of this right green triangle PDC plus the area of this green right triangle PQC. And again, we found out that three, that the area of the green shape equals to the area of the right green triangle PDC plus the area of the right green triangle PQC. So what is the area of the right green triangle PDC? The area of this right green triangle PDC equals to the base of the triangle that is PD times the height that is DC over 2. And again, the area of the right triangle PDC equals to the base that is PD times the height that is CD over 2 plus the area of the right triangle PQC. What is the area of the right triangle PQC? It is equals to the base that is PQ times the height that is QC over 2. And again, the right triangle PQC equals to the base that is PQ times the height that is QC over 2. So in total, the area of the green shape equals to the area of the right triangle PDC, that is PD. PD is 7 over square root of 10 times CD. CD is A, and A is 9 over square root of 10 divided by 2. So in total, if we found out that the area of the green right triangle PDC equals to 7, the base that is 7 over square root of 10 units times the height that is 9 over square root of 10 divided by 2 plus the area of the right triangle PQC. It equals to the base that is PQ, that is 2 times the height that is QC, that is 3 divided by 2. And again, the area of the right triangle PQC equals to the base that is 2 times the height that is 3 over 2. So in total, if we found out that the area of the green shape equals to 7 times 9 is 63, square root of 10 times square root of 10 is 10 divided by 2 plus 2 times 3 over 2. 2 over 2 is 1, so we left only with 3. So in total, the area of the green shape equals to 63 over 10 times 2 plus 3. So the area of the green shape equals to 63 over 10 times 2, that is 20 plus 3. So here we multiply 3 by 20 and then we divide it by 20 in order to overcome factor with this number. And we get here that the area of the green shape equals to, here in the numerator we have 63 plus 3 times 20 is 60 divided by 20. So the area of the green shape in total equals to 63 plus 60, that is 123 over 20. 123 over 20 is 6.15 square units. So again, if we found out that the area of this green shape equals to either 123 over 20 square units, so in terms of numbers, the area of this green shape equals to 6.15 square units. So finish with the first question. In the next step, I will present to you the second question, and we will solve it. Our mission in this second question is to find out the area of this ring shape. So in the moment we have quarter circle AOB. Those three angles, they're all right angles, according to what is given in the question. In addition, we know that OB equals to 5, that is to say the radius of this circle is equal to 5 units. And we also know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So, in order to find out the area of the green shape, we will do a construction, that is to say, we join points O and P together by a straight line. So what is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and then at point P, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this quarter circle, is equal to 5. So OP equals to R, that is the radius, that equals to 5. Likewise, we join points O and Q together by a straight line. OQ is also the radius of the circle, is equal to 5. So here we can implement all 20. So I'm going to quickly on all 20. According to all 20, in front of equal arcs, there are equal center angles. So in the moment we have a circle, and we have also arc AB, that is equal to arc CD. And according to this rule 20, in front of equal arcs, there are equal center angles. And because of the fact that arc AB is equal to arc CD, so in front of arc AB we have center angle alpha. In front of arc CD we have center angle beta. And according to this rule 20, because of the fact that arc AB is equal to arc CD, the center angle alpha and beta must be also equal to each other because of the fact that they are located in front of the equal arcs AB and CD. Okay, center angle alpha equals to center angle beta because they are located in front of the equal arcs AB and CD. So we can actually implement all 20 in our drawing. Why? Because in our drawing, arc AP equals to arc PQ equals to arc QB. In front of arc AP, we have this center angle MOP. In front of arc PQ, we have center angle POQ. And in front of arc QB, we have center angle QOB. And because of the fact that arc AP equals to arc PQ equals to arc QB, those three center angles must be also equal to each other in their sizes. So if we define the size of this center angle AOP as X, then the size of center angle POQ must be also equal to X, and the size of center angle QOB must be also equal to X. Well, because of the fact that those two center angles are located in front of the equal arcs AP, PQ, and QB. From the drawing, it is very easy to see that X plus X plus X, that is 3X, is equal to angle AOB. But it is given as a question that angle AOB equals to 90 degrees, and therefore 3X must be equal to 90 degrees. So let you know, 3X equals to 90 degrees. So here we divide this equation by 3 and finally get that the missing angle X equals to 90 degrees over 3, that is 30 degrees. So this is angle X, that is equal to 30 degrees in its size. side triangle AOP is equal to x is equal to 30 degrees in its size. Likewise, side triangle POB is also equal to x is equal to 30 degrees in its size. And finally, side triangle QOB is also equal to x is equal to 30 degrees in its size. So in the right triangle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 60 degrees in its size. Likewise, in the right triangle NQO, this angle equals to 90 degrees, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees, and therefore this first missing angle must be equal to 30 degrees in its size. In the next step, I copy this right triangle MOP and this right triangle NQO in a new page, and we prove that those two right triangles can go into each other according to angle side, angle rule. So hopefully, those are the two right triangles MPO and NQO that are going from the original domain. So in the next step, we prove that those two right triangles can go into each other according to angle side, angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees and therefore they are equal to each other. So hopefully, this is angle MPO. In the right triangle MPO, and is equal to this angle, this is actually angle NOQ. In the right triangle NQO. They are both equal to 60 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees and therefore they are equal to each other. So actually this is angle MOP in the right triangle MOP, and it is equal to this angle, this is actually angle NQO in the right triangle NQO. They are both equal to 30 degrees and therefore they are equal to each other. And finally, side PO equals to the right triangle NPO equals to side QO, the right triangle NQO. They are both the radii of the second is equal to 5 and therefore they are equal to each other. So I write it down. OP MP equals to OQ. It is the radius of the circle is equal to pi. So in total we can find out that those two triangles can go into each other according to angle side angle rule. We have those two angles, and the side that is included between those two angles is the side OP, the right angle NPO, are correspondingly equal to those two angles, and the side that is included between those two angles that is side OQ and right angle NQO. Therefore, those two right angles can go into each other according to angle side angle rule. So I write it down. Right angle NPO congruent, this is the side of congruent, to the right angle triangle NQO, according to angle side angle rule. And for the fact that those two right angles can go into each other, we derive that they have also the same areas. Okay? Any two right angles that can go into each other must have also the same areas. Okay, so therefore the area of triangle MPO is equal to the area of this triangle NQO. So I write it down. The area of this triangle NPO is equal to the area of this right triangle NQO. And again, the area of triangle NPO is equal to the area of triangle NQO. But it is very easy to see in the drawing that this is the right triangle NPO. The right triangle NPO consists of those two components. That is to say, it consists of the green quadrilateral MP between this point SS. So the right triangle MPO consists of the green quadrilateral MNSP, and it also consists of the right small triangle NSO. And therefore, the area of the right triangle MPO must be equal to the sum of the two triangles, to the sum of the two components that it consists of. This is to say, the area of this right triangle MPO must be equal to the area of the green quadrilateral MNSP plus the area of this triangle NSO, right triangle NSO. So I repeat again, because of the fact that the right triangle MPO consists of quadrilateral MNSP and also the right triangle NSO, the area of the right triangle MPO must be equal to the areas of the two components that it consists of. That is to say, it must be equal to the green quadrilateral MNSP plus the right triangle NSO. According to equation 1, the right triangle NQO equals to the right triangle NQO. So this is the right triangle NQO. It's very easy to see in the drawing that this right triangle NQO, this is right triangle NQO, consists of two triangles. It consists of this right triangle NSO and this triangle NSOQ. And therefore, the right triangle NQO must be equal to the sum of the components that it consists of. That is to say, it must be equal to the area of the right triangle NSO plus the area of this triangle SQO. So I write it down. The right triangle NQO must be equal to the area of the right triangle NSO plus the area of this triangle SQO. Again, because of the fact that the right triangle NQO consists of those two triangles, NSO and SQO, it means that the area of the right triangle NQO must be equal to the sum of the two components that it consists of. That is to say, it must be equal to the area of the right small triangle NSO plus the area of triangle SQO. So, this is equation 1. We have the area of triangle NSO on both sides of this equation 1, so we subtract the area of triangle NSO from equation 1. So, the area of triangle NSO will get cancelled, and we left only with the area of quadrilateral MNSP is equal to the area of triangle SQO. So if I found out that the area of this quadrilateral MNSP is equal to the area of this triangle SQO. So if you define the area of this quadrilateral MNSP as A, then the area of this triangle OQS must be also equal to A because they are equal to each other. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of this quadrilateral MNSP plus the area of this green shape PQS. Okay, again, I shall find out that the area of the green shape in total equals to the area of quadrilateral MNSP plus the area of shape PQS. But we already found out that the area of quadrilateral MNSP equals to the area of triangle SQO, therefore we can substitute the area of triangle MNSP by the area of this triangle SQO. And do it now, we get the area of the green shape in total is equal to the area of quadrangle MNSP, and the area of quadrangle NMSP is equal to the area of triangle SOQ plus the area of shape PQS. So if you follow the area of the green shape, the area of this green shape equals to the area of this triangle SOQ plus the area of this green shape PSQ. But the area of triangle SOQ plus the area of this green shape PSQ is equal to the area of sector POQ. So write it down. The rounded line above POQ is the sign for a sector. So this means that the area of sector POQ. So in total, we found out that the area of the green shape equals to the area of sector POQ. What is the area of sector POQ? Actually, the area of any sector equals to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector divided by 360 degrees. And therefore the area of sector POQ must be equal to pi r squared times the angle between the legs of sector POQ. The angle between the legs of sector POQ is 30 degrees over 360 degrees. The radius of this quarter circle r is equal to 5, therefore r squared must be equal to 5 squared, that is 25. So total pi r squared is 25 pi, and 30 degrees over 360 degrees is 1 over 12. So if we found out that the area of the green shape equals to either 25 pi or 12 square units in terms of numbers, is equal to 6.545 square units. So repeat again. If we found out that the area of this green shape is equal to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. So finish with the second question. And the next step, we'll summarize the lecture, and we'll start with the first question. The first question, our mission is to find out the area of this green shape. So in the moment we have square ABCD. This is angle PQC, that is a right angle. This is line 7 PQ, that is equal to 2 units in itself. This is line 7 QC, that is equal to 4 units in itself. Again, our mission is to find out the area of this green shape. So we know that ABCD is a square, so those 4 angles must be equal to 90 degrees on their sizes, and we know that all the sides of square ABCD are equal to each other, so we define one side of the left of one side of this square ABCD is A, therefore AB equals to DC equals to CB equals to PA equals to A. In the next step, we define this answer QB as x. So what is the left of AQ? AQ equals to AB, this is A, plus QB, this is X. So in total, AQ equals to A minus X. In the next step, we define the size of this against alpha. So in the right triangle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this coordinate angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, so this is the sum of the angles in any triangle. So here we know that AB is one side of square ABCD, and therefore AB is absolutely a straight line. So if you focus on this side of the straight line AB at this point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is equal to 90 degrees minus alpha, this angle is equal to 90 degrees, and therefore this first angle must be equal to alpha. 1 equals alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. This is the sum of the angles. Again, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. This is the sum of the angles on this side of the straight line AB, point Q. Okay, so this is again must be equal to alpha according to all 3. So in the right triangle AQP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this coordinate angle must be equal to 90 degrees minus alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I copy the right triangle APQ, this right triangle QBC in a new page, and I prove that those two right triangles similar to each other according to angle side angle rule. Firstly, those are the two right triangles APQ and QBC that are coming from the original drawing. So why those two right triangles similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can prove that all the angles in this right triangle APQ are correspondingly equal to all the angles of this right triangle QBC. And therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. And we derive that AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so here it is, over QB. QB is X, and it is equal to AQ, that is A minus X, over BC, that is A, and it is also equals to PQ, that is 2, over QC, that is 3. So in total, according to equation 1, we should found out that AP over X equals to A minus X over A, and it is also equal to 2/3. So here we have those two sides are equal to each other, so we get the equation 1 from those two sides that are equal to each other. So according to equation 1, AP over X equals to 2/3. Here we multiply this equation by X and find out that AP equals to 2/3 X. This is according to equation 1. Those two sides are equal to each other, therefore we get the equation 2 from those two sides that are equal to each other. So according to equation 2, A minus X over A equals to 2/3. Here, of course, multiply this equation, equation 2, and find out that 3 times A minus X equals to 2A. Here, we open the brackets on this side of this equation 2, and finally found out that 3A minus 3X equals to 2A. Here, we subtract 2A from this equation 4, and finally found out that 3A plus 2A is A, so A minus 3X equals to 0. Here we added 3X from the equation 3, and finally found out Put the equation in equation 2 and finally found out that a equals to 3x. In the next step, implement the right triangle QBC in a new page and implement the Badova story with right triangle QBC. After the right triangle QBC, that are going to the original drawing. This right triangle QBC, QC squared, that is the square of the opponent, equals to QB squared plus BC squared. QB is 3, therefore QB squared is 3 squared, that is 9. And it is equals to QB squared, QB is x, therefore QB squared is x squared, plus BC squared. BC is 8, therefore BC squared is a squared. So we actually found out that according to equation 3, 9 equals to x squared plus a squared. But according to equation 2, a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. So we can substitute a squared in this equation 3 by 3x squared from equation 2. We did it, and we found out that according to equation 3, 9 equals to x squared, and a squared is 3x squared. So in total, 9 equals to x squared, and 3x squared is 9x squared. So in total, according to equation 3, 9 equals to x squared plus 2x squared, that is 10x squared. So 9 equals to 10x squared. Here we divided this equation 3 by 9 and by 10. If I found out that x squared equals to 9 tenths. Here we took out all the equation 3, and found out that x equals to the square root of 9, that is 3 over square root of 10. According to equation 2, a equals to 3x. So a equals to 3 and x is 3 over square root of 2. So in total, a equals to 3 times 3 is 9 over square root of 10. So a equals to 9 over square root of 10 units in its length. This is side DC of square ABCD, that is equal to a, and a equals to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. So AP equals to 2/3 and x is 3 over square root of 10. So in total, AP, we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and finally found out that AP equals to 2 over square root of 10. AP equals to 2 over square root of 10. And A equals to 9 over square root of 10. So, what is the length of PD? Although it is very easy to say that PD equals to AD minus AP. Read again. PD equals to AD minus AP. So PD equals to AD, that is A, and A equals to 9 over square root of 10 minus AP. AP is 2 over square root of 10. So in total, PD equals to 9 over square root of 10 plus 2 over square root of 10, that is 7 over square root of 10 units. So we found out that PD equals to 7 over square root of 10 units in its length. In the next step, we join points P and C together by straight line. By joining points P and C, we can do 2 right triangles. Right green triangle PDC, this right green triangle PQC. Because of the fact that the green shape consists of exactly those 2 right triangles, PDC and PQC, it means that the area of the green shape must be equal to the sum of the areas that it consists of. That is to say, it must be equal to the area of this right green triangle PDC plus the area of this green right triangle PQC. So I write it now. We actually wrote it down actually, and found out that the area of the green shape in total equals to the sum of the areas of the 2 components that it consists of. That is to say, it must be equal to the area of the green right triangle PDC plus the area of the green right triangle PQC. what is the area of the right triangle PDC? It is equal to the base PD times the height DC over 2. And it is PD times DC over 2 plus the area of triangle PQC, that is the base PQ times the height that is QC over 2. And it is the base PQ times the height QC over 2. PD is 7 over square root of 10, CD is 9 over square root of 10 divided by 2. PQ is 2, QC is 3 divided by 2. 7 times 9 is 63, square root of 10 times square root of 10 is 10 divided by 2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, we left only with 3. So in total, the area of the ring shape equals to 63 over 10 over 2 plus 3. 63 over 2, 63 over 10 over 2 is 63 over 10 times 2 plus 3. So it is 63 times 10, 63 over 10 times 2. 10 times 2 is 20, so in total this expression equals to 63 over 20 plus 3. Here we multiply 3 by 20 and then we divide it by 20 in order to account factor of this number. So in total, in the numerator we have 63 and 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. So in total, if we found out that the area of this ring shape equals to either 123 over 20 square units, or in terms of numbers, the area of this ring shape equals to 6.15 square units. So we finish with the first question. And the next step, I'll present to you the second question and we solve this. In the second question, our mission is to find out the area of this ring shape. So, in the drawing, we have quarter-circle A or B. Those three angles are all right angles. We know that OB equals to 5, that is to say the radius of this quarter-circle is 5. In addition, we know that arc AP equals to arc PQ equals to arc QB, and our mission is to find out the area of this ring shape. So first of all, we can implement here all 20. So I put figure rule 20. According to rule 20, in front of equal arcs, there are equal central angles. So in the drawing we have a circle. And we know that arc AB is equal to arc CD. And therefore, according to this rule 20, in front of those two equal arcs, there are equal central angles. That is to say, central angle alpha equals to central angle beta. So those two central angles are equal to each other because of the fact that they are located in front of those two equal arcs. So we can actually implement rule 20 in our drawing. In our drawing, we have arc AP equals to arc PQ equals to arc QB. So in front of those two equal arcs, we have also equal central angles. That is to say, those three central angles that are located in front of those two equal arcs must be equal to each other in their sizes. So if you define the size of this central angle as x, then the size of this central angle must be also equal to x, and the size of this central angle must be also equal to x, because of the fact that they are located in front of equal arcs. So we have so we have x plus x plus x in total the sum of those three center angles is equal to the big angle AOB. But the big angle AOB equals to 90 degrees, and therefore 3x equals to 90 degrees. 3x equals to 90 degrees. Here we divide this equation by 3 and finally found out that the size of one angle x is 90 degrees over 3, that is 30 degrees. So center angle AOB and center angle AOP equals to 30 degrees in size, center angle POQ equals to 30 degrees in size, and center angle QOB is also equal to 30 degrees in size according to Rule 20. So in the right triangle MPO, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this 30 degrees angle must be equal to 60 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in this right triangle NOQ, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees, this angle equals to 90 degrees, and therefore this 30 degrees angle must be equal to 30 degrees in size. The next step, before we did we implemented Rule 20, in the drawing we joined points O and P together by straight line. OP is the radius of the secant, that is 5. We joined also points O and Q together by straight line. OQ is also the radius of the secant, that is equal to 5, according to what is given as a question. In the next step, I copy the right triangle NPO, this right triangle NOQ on the new page, and prove that those two right triangles can go into each other according to the side angle rule. So actually, those are the two right triangles NPO and NQO that are going to the original drawing. So why those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees, and therefore they are equal to each other. And finally, OD equals to OQ, they are both the radius of the secant, that is equal to 5, therefore they are equal to each other. So I can prove that those two angles and the side that is included between those two angles, that is side OP in the right triangle NPO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is side OQ in the right triangle NQO. And therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of the right triangle MPO is equal to the area of the right triangle NQO. But the right triangle MPO consists of two components. It consists of this green quadrilateral MNSP and this right triangle NSO. And therefore the area of the right triangle NPO, the area of the right triangle MPO must be equal to the sum of the areas of the two components that it consists of. That is to say, the area of the right triangle MPO must be equal to the area of quadrilateral MNSP plus the area of the right triangle NSO. Likewise, if you focus on this right triangle NQO, this right triangle NQO consists of two components. It consists of this right triangle NSO, and it also consists of this triangle SQO, and therefore the area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the right triangle NSO plus the area of triangle SQO. So in this equation 1, we have the area of triangle NSO on both sides of the equation. So we subtract the area of triangle NSO from equation 1, and therefore the area of triangle NSO will get cancelled, and we left only the area of triangle of quadrilateral MNSP that is equal to the area of triangle SQO. This is quadrilateral MNSP, and the area of this quadrilateral MNSP is equal to the area of this triangle SQO. So if you define the area of the given quadrilateral MNSP aside, then the area of triangle OSQ must be also equal to A because they are equal to each other according to equation 1. Our mission is to find out the area of these green shapes. What is the area of the green shape? For the drawing it is very easy to see that the area of this green shape equals to the area of quadrilateral MNSP plus the area of this green shape PQS. Again, from the drawing it is very easy to see that the area of the green shape equals to the area of the green quadrilateral MNSP plus the area of the small shape PQS. But we already found out that there are this quadrilateral MNSP is equal to the area of this triangle SOQ. Therefore, we can substitute the area of this green quadrilateral MNSP by the area of this triangle SOQ. Again, we substitute the area of this quadrilateral MNSP by the area of triangle SOQ. And the total actually found out that the area of the green shape equals to the area of triangle SOQ plus the area of shape PQS. And again, the area of this green shape equals to the area of this triangle SOQ plus the area of this small shape PSQ. But the area of the small shape PSQ plus the area of this triangle SOQ equals exactly to the area of sector POQ. With again, the area of triangle PSQ, the area of shape PSQ plus the area of this triangle SOQ in total is equal to the area of sector POQ. So in total we shall find out that the area of the green shape equals actually to the area of sector POQ. So what is the area of the sector POQ? Actually the area of any sector equals to pi r square, that is the area of the circle that contains the sector, times the angle between the legs of the sector over 360 degrees. And therefore the area of sector POQ must be equal to pi r square times the angle between the legs of the sector that is 30 degrees over 360 degrees. Okay, again, the area of the green shape in total equals to the area of sector POQ. The area of sector POQ equals to pi r square, that is the area of the sector that contains the sector, times the angle between the legs of the sector. Angle between the legs of the sector is 30 degrees or 360 degrees. So this pi r square times 30 degrees over 360 degrees. R is the radius of the quarter second, that is 5, therefore r squared is 5 squared, that is 25. So in total this expression equals to 25 pi, and 40 degrees over 360 degrees is 1 over 12. So in total we have found out that the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 12 square units, so in terms of numbers, the area of this circle and the area of this green shape is equal to 6.545 square units. Okay, thank you very much.